we're going to make this even more operational to do the statistics part of looking at regression and the line. I gave you the model, I gave you the thinking, I gave you the computational method to find the line and to estimate the parameters, which is finding the line and the residuals from the line, average residuals, and I gave you the statistical sampling distribution, sampling errors of the slope and the intercept. Now, what we've done always in the course, and which we will do again now, we will take those sampling errors and turn them into hypothesis tests and confidence intervals. That's what we use those sampling errors for. So here it comes. We can do hypothesis testing just like we have done for a mean or two means. We can do that for either the slope or the intercept. That's just what you should read here. It could be a hypothesis related to the slope, or it could be a hypothesis related to the intercept. Either would work. And then we are basing our statistics, be it hypothesis testing or be it confidence intervals, based on the additional theorem on top of what I already told you, that assuming the null hypothesis, that's the usual scenario line of thinking for hypothesis tests, that if the hypothesis is true, we know what the sampling error, what the sampling distribution is, thoroughly standardized. If I take, say, the intercept, the computed slope, goddammit, the computed slope, subtract the hypothesized slope, divide by the standard error of the slope. So I have a standardized error. This theorem tells us what would be our expectations, exactly the same theorem that we had for a mean or the difference of two means, that such differences behave like a t-distribution if I standardize them. So the standardized sampling error is a t distributed like a t-distribution. The right t-distribution, the one with n minus 2, the 2 comes from that the mean now consists of both the slope and the intercept, not only just one mean. It's not a proof, but that's how how we can maybe see the analogy. And then we can do hypothesis testing. First of all, where do we see the results in R? Well, I'm not gonna, or should we maybe, let's actually just, yeah, let's go and do it actually. Like that, away with you, like that, go back. Did I actually do a fit already? Yes, I did. Why don't we do it on the original data here, height and weight, summary, there we are. We looked at it already, now I'm doing it in R. Those hypothesis tests, or at least some hypothesis tests, look at the, here's the intercept again, 1 kilo per 1 centimeter, right? Thank you, the slope again. I'm gonna practice intercept slope there, okay. Slope! Slope is 1.1 kilogram per centimeter. The standard error, the sigma slope, that is 0.1 centimeter. When I take, and that's the hypothesis test for the hypothesis of the slope being 0. By default, R is producing 2 hypothesis tests for us that is shown in those 2 t. So these are actually 2 t ups values. It's not quantiles, it's observed t statistics, where you take the 1.1 and you divide by the 0.1. That's roughly 10, as you can see. So it's the estimate divided by the standard error, the uncertainty of the estimate, and the beta 0 here is then 0, right? These are the two hypothesis tests that are given by R by default. It makes quite good sense for the slope, maybe less so for the intercept. So let's not talk about the intercept. Let's talk about the slope. Now this was 4 in a row in the right way, so we're improving. Testing whether the slope could be 0, to say it like that, makes some kind of sense, because that's the null hypothesis of no relation between x and y, right? Maybe that's a good hypothesis to make. Is there a relation statistically between our x and y? Well, I make the hypothesis there is no relation, 0 slope. Can I reject that hypothesis? Yes, I compute the t-statistics. It's 10.5. We know by now a t-statistic of 10.5, that's a large one, because t-statistics should be within plus minus 2 roughly, not to be large. Right? So if I have something if I have a signal that goes as large as 10 on the t-scale, well, the p-value is already found to me. Here, it's a very small p-value. I could have found that p-value myself by doing pt on 10.504. That's the probability of being less than. So maybe I should go 1 minus that. That's the probability of going to the right, even larger. And then I should, because it's the classical non-directional test that we exclusively do in our course. Yeah, that's a classical error to make. Let's see what it tells me. Actually, sometimes it's good to read what R is telling you when you make an error. Argument df is missing. Ah, of course, this is not a normal. I should give the df. What's the df? 8. I could actually also find it here. 10 minus 2. Check. Exactly that p-value, right? So it just goes check in the right t-distribution to give us the p-value. Have I documented that there is a relation between height and weight now? Weight and height? Yes, I have. Can I reject the hypothesis of no relation? Yes, I can. I have pretty strong evidence against the idea that weight is not related to height. So I believe weight is related to height, right? That's the line of thinking. It can be done also for the intercept, but it's not very interesting to test whether our weight at 0 centimeters is 0. I don't care about that. So very often intercepts are not so interesting, actually. They're just there to make things match up somehow. That was hypothesis testing. We can just the same way do confidence intervals. So now you can see the speed is a bit up now. When we started, we spent a whole day talking about a single confidence interval, and then we spent a whole double lecture speaking about a single hypothesis test. Now I just gave you actually a couple of 2, 3, 4 hypothesis tests in a few minutes, and here are 2 confidence intervals in 30 seconds, because now we're getting used to it. And it's the same shit all over, right? It's the slope plus minus 2 standard errors of the slope. Do you remember the American? Well, Arthur Benjamin, TED Talk, plus minus 2 standard errors. Here we go again. We don't use 2, we use the t-quantile to be as intelligent as possible. So that's basically it. We can read off those standard errors from the R output. I showed you that. I'm going to recap that again in a sec. I'm going to actually skip this one. Maybe just a few words. You can find it in my R code. It's just as a way to let us again use the simulation ability to think about what is actually happening in the theory and the methods that I'm giving to you. In this case, I am trying to do something quite similar to before. I'm many times, well, 100, could put it at 1,000 or 10,000. I am trying to do a linear regression, and then each time I extract the confidence interval. And then I count how often do my confidence interval actually hit the truth, right? I can actually count how often will my confidence interval, that's the dance, you know, I'm not going to do it. The confidence interval dance. The confidence interval changes in position. When you get tired in the legs, you can just do the arm dance. And then the width, right? This is where we count. And then we will see that on average, the confidence interval will hit the truth in 95% of the time, because that's the definition of the method of confidence intervals, that it's a random interval which has on the long run the interpretation that it hits the truth in 95% of the time. So I would just put the words on that and not actually do it, because we need to do something more fun. Here we are. Let's see how it goes. We continue the game. 2 questions now. You do the rendering. Hat means hat, right? So see a hat in front of you when you see the red hat. The A plot was the only one with a negative mean, right? And the slope was negative. And the sampling distribution will sort of distribute around the slope itself, the value of the slope, right? So it was the one with the where that topped on the negative side, that was the A. Show image. I didn't realize I had this little feature. That's, of course, obvious. Nice. So here they are. The A had the negative, right? It was centered around something negative, whereas the other, this is centered around 10, this is centered around 0. This is definitely a negative slope, so that could be the only reasonable answer here to the question. I have one more for you in the same line of thinking. King here is still on the top. This is the expression hat minus truth divided by sigma. So it's the same expression on the slide, but in a low-key way. Remember the theorem I gave you for that. This is what the theorem talked about, the difference between the estimator and the truth relative to the standard, to the sampling error of that one. That's a t distribution. A t distribution is centered around 0, like the standard normal. So it could only be c here. We don't, and then forget about the actual size of the standard deviations, it could only be c here. Good job there. Is there is there a problem? Well, not that I can do anything about it if there were, but anyway.